Alright, in this video I'm going to do a quick overview of quantum mechanics, at least as far as it applies to chemistry. I'm not going to go into like the wave equation or anything like that. In fact, when talking about quantum mechanics, you always hear about things like the wave-particle duality, and everybody likes to sit around and talk about, oh wow, what does that mean about reality, and are we in a simulation, and all this other sort of philosophical pothead crap. But really, that's all interesting and everything, but when it comes to practical purposes, the wave particle duality pretty much just means if the situation calls for me to think about it like a wave, then I'm going to treat it like a wave. And if it's a situation that calls for me to think about it like a particle, then I'll think about it like a particle. So you can just kind of choose which one makes whatever you're talking about easier. So for instance, when we're talking about quantum states, which is what I'm going to be covering in this video, we start off with the energy level, which is which is represented by N. So that's the energy level of an electron inside of an atom. So if we think about an atom like particles, because that's easier to do in this case, we can think about it in the Bohr model with a nucleus in the middle and then an electron sort of traveling around the outside in an orbit. So we can think of this as an energy level. If there's no energy level between this and the nucleus, then this is the energy level N equals 1. And you can do that for multiple different atoms. For instance, if we think about the helium atom, it has an energy level. The relative size of these don't take that into consideration. It's just my crappy drawing. So this would have 2 electrons. But then we can also think about it in terms of multiple energy levels. So if we're thinking about our hydrogen atom as particles, and we have this energy level, and we have this energy level, and where our 1 electron is in that energy level, if we add energy to it, and it has to be a certain amount of energy, it has to be what's called a quantized amount of energy, which is why it's called quantum mechanics, then this energy level, this electron in the lower energy level will actually jump to the higher energy level, and then we have N equals 2. So that's how the energy levels work. The N equals 1 represents the lowest energy level, and the N equals 2 represents the next higher, and then we can go to N equals 3, 4, 5, so on, as high as you want. For all practical purposes, it's going to be finite, but, there's no mathematical reason why it needs to be finite. So then we get to our next quantum number, which is represented with L. And instead of just drawing a single line, I'm going to draw my crappy looking fancy L. That's the angular momentum. And sometimes you'll see it written as azimuthal. And that just has to do with things like polar coordinates, which I'm not going to get too into. I'm going to not get that deep into the mathematics of quantum mechanics here. So L is always equal to, or it's not always equal to n minus 1, but that's the highest it can be. So for instance, if n equals 1, then L must equal 0. And if n equals 2, then L can either equal 1 or 0. And this angular momentum number you can sort of think of as determining the shape of what's called the orbital. These orbits around the atom are called orbitals, or actually the electron is occupying an orbital. So for instance, in this one, the electron, there are 2 orbitals in this energy level, and we'll get to why there can be 2 here. But anyway, these are called orbitals. These electrons are occupying orbitals. So this angular momentum number determines the shape of the orbital. So with hydrogen, we had n equaled 1 and L equals 0. And the shape of this sort of orbital is, and see now I'm going to go from treating it like a particle to treating it like a wave. The shape of the orbital is sort of this spherical cloud where the electron has a probability of occupying any space within this cloud. And for all intents and purposes, where the electron can occupy actually kind of goes off to infinity, but for practical purposes, we think about it as occupying this sphere around the nucleus. So then if we have n equals 2 and L equals 0, we get a different sort of shape of this cloud that actually has this area in the center called a node, where the electron can exist inside the node and it can exist outside the node, but it actually doesn't exist anywhere on this line here, which is another one of those, weird sort of philosophical, what even is reality kind of things. How does the electron exist here and here, but it doesn't exist in there? But, that's for people to sit around and ponder on their own. I'm not going to go into that too much. But then if we get to n equals 2 and L equals 1, we will end up with, and this doesn't actually exist in the hydrogen atom, but just for illustration purposes, you end up getting a shape that has these 2 sort of dumbbell-looking clouds on either side. And once again, it's this weird thing. Wow, it doesn't exist in the middle, but it can exist in both of these parts. But yeah, that's how it exists. And we'll get to why this, or not why, but this is called a p orbital, and this is called an s orbital. So this would be a 1s orbital, and this would be a 2s orbital, and this is a 2p orbital. Then there can actually be up to 6 of these p orbitals, and you write it like this, so it's the 2p orbital, and there's up to 6 of them. There can only be 2 that occupy it when it's in this orientation. So there are 2 other orientations, and we get another quantum number to represent the orientation, and that is the magnetic quantum number. Sometimes just M, sometimes it has an ML, so that's the magnetic quantum number. And this quantum number always ranges from negative L to positive L. And this, like I was just saying, determines the orientation of these orbitals. So, for instance, like I said, we have the s orbital. There's really no orientation for the s orbital because that will equal n equals 1, and it's always going to be L equals 0 if it's an s orbital, and so m equals L can only equal 0 because it has to range between negative L and positive L. So this is the s orbital. Then if we go to the p orbital, that can only exist in n equals 2 because L has to be, it can only go up to n minus 1. So n has to be 2 in order for L to equal 1. And then ML can equal negative 1, 0, or 1. That's the p orbital. And with that, we get this first type of p orbital, which would be, sorry, this should be the same size. So that would be n equals 2, that's L equals 1, and then ML equals minus 1. And then we have this other orientation, like this, which would be L equals 1, and ML equals 0. And then we would have this other orientation, which, if you can picture it sort of coming out of the page and into the page, this would be L equals 1 and ML equals negative 1. So you see, or wait, positive 1. So you see that at ML in the p orbitals, these are all p orbitals. The ML ranges from minus 1, 0 to plus 1, while L remains 1 when it's a p orbital, because the L determines the shape, where the ML determines the orientation. So earlier I talked about how there's 6 electrons in these p orbitals, but we see there's only 3 orbitals. So each of these must contain 2. And sort of, I guess what I have left unspoken was this idea of what's called the Pauli exclusion principle, which says that within an atom you could not have 2 electrons occupying the same orbital. Both electrons, or all the electrons, all E, and this is often how you'll see electrons represented, all electrons have unique quantum numbers. So if we have only 3 p orbitals but 6 electrons can occupy them, it looks like we need yet another quantum number. That's S equals spin. And spin is one of those things that if you learn quantum mechanics, you start thinking, well, what is spin? And you get into sort of the deep rabbit hole of what spin is, because you'd think, because they called it spin, that it would be something simple like, spinning. But I think spin actually comes more from spinors, which are used to describe the inner states of electrons. But I won't get into that. So spin, for our purposes, we're not going to talk about what it actually means, only that spin can equal either minus 1/2 or plus 1/2. And so you see how we get the extra quantum numbers that we can use to place the two electrons into each of these p orbitals. So this would have a spin plus 1/2 and spin minus 1/2, and this would have a spin plus 1/2, spin minus 1/2, and this would have a spin plus 1/2, spin minus 1/2. So, and don't get confused about the fact that there are two lobes on this. There isn't like a spin plus up here and a spin minus down here. The spin plus and spin minus occupy the whole thing. So when we add this spin, this makes it so that electrons in an atom will begin doubling up. So if we have an atom, I won't name what atom it is. I'm going to go over in the next video the various types of elements that we're going to care about. But if we want to fill this atom, if we want to fill the orbitals on this atom, first we put one electron in, and in this shell it would be the n equals 1, so L equals 0, so ML must equal 0, but spin can be plus or minus 1/2. So we can add another one where one electron is spin plus 1/2, the other is spin minus 1/2, and this is the only allowed number of electrons that we can have in this atom, or in this shell of the atom. So if we want to add another shell, so I'll just do that over here. Well, I won't show the lower shell on it. So for this, we can add these, which would be the n equals 2, and then L equals 0, ML equals 0, spin plus or minus 1/2. So we have these in our next shell up. But then in the next shell up, we also have n equals 2, where L equals 1. Therefore, therefore ML can equal minus 1, 0, or plus 1, and spin can equal plus or minus 1/2. So this means we have 1, 2, 3 different shapes, or different orientations of the L equals 1 shape, but then we multiply that 2 because we can have 2 different spins for each of them, and so we end up with these 3 extra pairs. And it's important to think about these electrons as pairs as well, where one of them is the plus 1/2 and one of them is the minus 1/2. But with these 3, when you're looking at the atom, usually if you're looking at, say oxygen and I'll go over this a little bit more in the next video, you'll see it written like this, and there's no way to really differentiate the electrons. We're not treating the s orbital electrons different from the p orbital electrons, but this is just how we fill our electrons into the atom. And the way we fill it into the atom also, if we have an atom that in our second and our n equals 2 level has just a single electron, then we put it like that. Now if we have the next atom over in the periodic table, we need to add another electron. We don't start pairing it up right away. We add it by itself. Then a third electron, we add it by itself, and the fourth electron, we add it by itself, and only then do we start pairing them up, because electrons are all negatively charged, so they repel each other. So I think this is called the off-bow principle, if I'm not mistaken. I always think about it as the bus seat principle, where if you're on a bus, like a city bus, every seat is going to fill up with a single person before the bus starts filling up even more, and then you have to start doubling people into the other seats. Everybody wants to sit alone. These electrons also want to sit alone. They're a bit antisocial, sort of like me, so you want to fill it up that way, which is why with this oxygen you see I have this pair here and this pair here, because we filled up 4 and then we added 2 extra ones to make these pairs, and then we end up with these lone electrons, which in the next video when I go more into bonding will start making more sense. Okay, so now we're going to start building up our atoms by looking at the electrons in them. So, because carbon is such an important one in biochemistry, I'm going to start with carbon, and we want to build up the electrons in it in the way that I had shown with the quantum numbers. So carbon we see has 6 protons, which means if we want it to be neutral, it needs to have 6 electrons. So it's going to have 2 in the inner shell, then it's going to have 4 in the outer shell, so that equals 6. And in the next video I will talk about why this property is important of having these 4 lone electrons in the outer shell. But for now we can say that carbon, with the electrons as we built them up in the orbitals, so first in these 2 in the inner shell are going to be the 1s, and we use a superscript 2 to show how many there are. And then in this outer shell we will first start with the 2s, because we fill those first, and there are 2 of them, so we put another 2 there, and then we have 2 left, which will be our 2p, because it's 2 because it's in the second shell up. But then we have 2 of them, so we put a superscript 2 there. We see that 2, 4, 6 equals 6 electrons, which is the same as our 6 protons, so that makes it neutral. Then if we go to the next one over, we have nitrogen, which has 1 extra electron because it has this 1 extra proton. So we start with our 1s2 and then our 2s2, but now we have 3p, or it's in the second shell, but we have 3 of them, so we put a 3 here. That's 2, 4, 5, 6, 7, so that's 7 electrons to neutralize our protons. And then we can do the same thing with the oxygen, and that has 1 extra electron, so it has 1s2, then 2s2, then 2p4, so it has 4, 5, 6, 7, 8. Just like it has 8 protons to neutralize, it has 8 electrons. So then if we see, what's interesting with the periodic table is this sort of build-up where we have the 1s, the 2s, and the 2p are all going to be in this second row down. So we count the hydrogen and helium as the first row, or the first row that's enumerated there. Then the second row will have these 2 s's, and then once we get over here it has 2 p's. The lithium and beryllium will have 0 of the 2 p's, which is why they're over here, and they only have 2s1 and 2s2. But now if we go down to the third row, if we want to look at something like, let's say, sodium, then sodium, which is Na, is going to have 1s2, 2s2, and it's going to have all of the p orbitals in in the second shell, so it'll be 2p6, but then we add one more, which is going to be the 3s, and it only has one of them. That's why it's all the way over here on the left side. So it has this 3s1 here. However, since we added only one more proton going from neon to sodium, then but we go up one whole shell. So it's like if we have our nucleus down here, we have our first shell, our second shell, and our third shell. We only increased this positive charge by one more proton, but then we increased our shell by this much, by quite a bit of energy, so it doesn't hold on to this 3s1 very tightly. So with sodium, we end up getting this positive ion quite often, which will have 1s2, 2s2, 2p6, which if you see, if we lose this one electron, this gives it the same electron configuration as neon, which in this reading left to right sort of way, it gives it the neon electron configuration, but since it has that one extra proton, it makes it positively charged. It makes it a positively charged ion, and sodium is fairly stable as a positively charged ion. Now, if we go all the way over on this third row and look at chlorine, so that will actually have 1s2, 2s2, 2p6, and then it has these p orbitals, or it has two s orbitals in the third shell, so it has 2s3, and then it also has 1, 2, 3, 4, 5 p orbitals in the third shell. This, I got this backwards. This should be 3s2, then 3p5. So you can see that this isn't a full p, but because sort of in the opposite way of the sodium, we're staying in this third shell, but now we've added a whole bunch of positive down here. We've added a lot of protons to our nucleus, so it's actually going to be pulling even harder on this third shell. So quite often, chlorine, and I'll write it over here, ends up with a negative charge, and that will have the 1s2, 2s2, 2p6, 3s2, 3p6. So that's the chloride ion, and that has the same electron configuration as argon. So quite often when writing these electron configurations, because once you start getting up here in these really high numbers, you start having a lot of electron configuration, a really large electron configuration. So a way you can actually shorthand it is, let's say you were going to write chlorine, not the chloride, but the chlorine down here. You could actually write that as, so you go back to this one here, so it would be neon. I think you usually write that in brackets, so you just write neon, and that just tells you that neon is the electron configuration all the way up to the third shell. So then we have our 3s2, 3p5. So you can just write it like that. In biochemistry, we don't write these electron configurations like this very often. It doesn't come up that much, so this is just sort of a sidebar of general chemistry type stuff. But it's good to know, and it's good to know about these electron configurations, particularly when it comes to this this shell sort of concept about how when you start over here, you move up a shell, but you don't gain that much in the nucleus as far as positive charge. So things on this side over here, these two columns here, are oftentimes seen as positively charged. And in fact, in this column, they're often a positive 1 charge. So you'll get sodium plus and potassium plus. And then once you get to this second column, you actually start losing both of these s orbitals that are at the very highest shell. So you end up seeing magnesium 2 plus and calcium 2 plus. And then over here, you don't see negative that often with things prior to this column right here. So it's quite often that you see fluoride as an ion and chloride as an ion, and bromine doesn't come up too much in biochemistry, but we do have iodine. So you can see that with the periodic table, in these different columns, we get these similar sort of electron configurations based on what column it's in, which gives it a similar sort of chemistry. And then in the rows, what you're seeing is just an increase from one to the next of protons, and so you're just adding 1 electron to the configuration on each one. So that's sort of one of the useful ways of reading the periodic table. It's not set up in this sort of weird shape just for artistic reasons or anything. It's set up this way because it actually has, a powerful meaning. A lot of chemistry is just learning how to read the periodic table, because there are a lot of different periodic trends, they're called, which I'll go into a little bit more in the next video. But there are trends you can read in the periodic table. So this is one way that we can read the periodic table, is setting up these electron configurations. And in the next video, I am going to talk more about hydrogen, carbon, nitrogen, and oxygen, and the sorts of bonds that we can find in those, and the chemical properties of them within molecules. And that will start getting us more into the chemistry side of things. So I will see you in the next video.